Chemistry, the Central Science, Chapter 4, Reactions in Aqueous Solutions, Lesson 2. So this lesson deals with acids and bases, and we can look at some typical properties. Acids tend to taste sour, so when we eat citrus fruit, citric acid is in there, which makes it taste sour. It causes a color change in plant dyes, which is the same for bases. It will just change it in a different way. Acids can react with certain metals to form hydrogen as a gas. It reacts with carbonates to make bicarbonates, or it reacts with carbonates and bicarbonates to make CO2. So that's, your typical volcano science experiment when you're a kid. You mix vinegar and baking soda, and it's CO2 bubbles that are formed. And aqueous solutions will conduct electricity, just like with bases. Now, on the contrary, bases have a bitter taste. They feel slippery, and they can react with fatty acids to make soap. So there's two different types of definitions of acids and bases. The Arrhenius acid definition says that it's going to increase the amount of hydronium ion concentration in water. So this is our hydronium ion. The Bronsted acid is simply what we would call a proton donor. But when we say proton, we're talking about an H+. So in this example, hydrochloric acid donates a proton to water to create the hydronium ion and the chloride ion. So it's a proton transfer. An Arrhenius base will increase the concentration of the hydroxide ion, which is shown down here. A Bronsted base is then going to be a proton acceptor. So an acid will donate and a base will accept. So down here we have ammonia, which is a base, accepting a proton from water, which then water acts as the acid, to form the ammonium ion and the hydroxide ion. So the difference here in these, hydrochloric acid is a strong acid, which is why we see the arrow only going in one direction. Ammonia is a weak base, which means that this goes back and forth. And more often than not, it's just going to exist as NH3 as opposed to the ammonium ion. So there's a list of strong acids and strong bases in your textbook, and here's another table I've provided. So your halogens, when they form acids except for fluorine, will all be strong: nitric acid, chloric acid, perchloric acid, and sulfuric acid. So basically, if you're not on this list as a strong acid, then you're a weak acid. Our strong bases are going to be all soluble metal hydroxides. So here we can see all alkali metals, which a group 1 metal hydroxide will be considered a strong base. And then some of your group 2 metals, calcium, strontium, and barium. So all other metal hydroxides are actually insoluble, which is why they would not be considered strong bases. And your weak bases are going to come from some sort of derivative of the ammonia compound. So we can identify strong and weak electrolytes by looking at, do these substances actually completely dissociate in water, or do they not? So if you are a soluble ionic compound, you will be a strong electrolyte. If you're a strong acid or a strong base, you're a strong electrolyte. Then the only things that are considered weak electrolytes would be weak acids or weak bases. So here, when I look at this ion or this ionic compound, I know it's ionic because it starts with the metal. So this is the potassium bromate. I know that potassium is always soluble, so this salt would be a strong electrolyte. HNO2, I recognize this as an acid. I go back to my strong acid list. It is not listed. Therefore, it is a weak acid and a weak electrolyte. Here we have methanol, which, even though there's an OH here, this is not considered a base. And because this is a molecule, it's not going to dissociate into anything in solution, and therefore it happens to be a non-electrolyte. So when you look at something and you see a group of nonmetals all bonded together, and we're not looking at something that would be an acid where the H shows up first, this is always going to be a non-electrolyte. HI is hydroiodic acid. We look at our strong acid list and see that, yes, it is on there, so it is a strong electrolyte. Zinc sulfate, it is a soluble compound. We can split apart the zinc from the sulfate, so this would be a strong electrolyte. Once again, here, this is the chemical formula for urea. I see a whole bunch of nonmetals bonded together. It is not going to dissociate or separate into ions in water, therefore it would be considered a non-electrolyte. So for review, strong electrolytes are any strong acid, strong base, or soluble compound. Your weak electrolytes are weak acids and weak bases. Your non-electrolytes would be molecular compounds. So we can talk about the different types of acids. Monoprotic, meaning that it's only going to give one proton. And we've listed some strong electrolytes and strong acids first. So hydrochloric acid is a strong acid, nitric acid is a strong acid. Then our next acid is acetic acid. It's not on our strong acid list. It is monoprotic because it only gives up one H, but it's considered a weak electrolyte. So in looking at a dissociation equation, you can simply tell if the arrow goes one way, it's strong. If the arrow goes both ways, it is weak. Diprotic, meaning two protons can be potentially given up, but they always happen in a stepwise process. So the first dissociation from sulfuric acid is a strong electrolyte because it's a strong acid. However, the next proton, when it dissociates, it is considered a weak acid because the arrows show us that it goes back and forth, which means that it stays together more often than it is separate. And your last type of acid is a triprotic acid, meaning three protons can be given away. Once again, this happens in a stepwise process. So phosphoric acid is a weak acid among each of its steps. So it is considered a weak electrolyte every time that it goes to dissociate a proton or give one of its protons away. So the reaction that occurs between acids and bases is called a neutralization reaction because we're neutralizing the power of the acid and the base to form water. So as stated, our hydronium ion is your H3O plus, your hydroxide ion is your OH minus. These are the substances that are truly acting as your acid and your base in solution. So when we mix these two things together, and if we have a strong base, you're always going to form some sort of salt, which is an ionic compound, and water. So for example, hydrochloric acid reacts with sodium hydroxide to form sodium chloride and water. So what's really happening here, if we look at the net ionic equation, we know that aqueous substances will completely dissociate in water to form their ions. So we get an H plus, we get a Cl minus, we get an Na plus, we get an OH minus. Sodium chloride is a soluble salt, so it dissociates into Na plus and Cl minus. Water is a liquid, so we do not separate it. If we cross out like terms, we see then that what's really happening is the proton reacts with the hydroxide ion to form water. So practicing with neutralization net ionic equations, write the balanced molecular net ionic equation for the neutralization reaction between solid aluminum hydroxide and aqueous sulfuric acid. So even though aluminum hydroxide is insoluble in water, it can be dissolved in a strong acid. So we look at how do these things dissociate? Well, aluminum is an aluminum 3 plus. This gives us an OH minus. We know our protons come off as an H plus, and then we're left with the sulfate ion. So we're doing an exchange reaction or a double displacement. So then the aluminum ends up with the sulfate and the hydrogen ends up with the hydroxide. We do our crisscross process and see that we form aluminum sulfate, which that 4 should be subscript. Aluminum sulfate, which is aqueous because our solubility rules say so. And then we get water because H and an OH, HOH forms water. So then we go back in and we balance our equation, keeping in mind I have 2 aluminums here, so I have to have 2 over here. I have 3 sulfates, so I need 3 sulfates. And then I look at, I have a total of 6 H's here. I have a total of 6 H's here, which means 12. So then I have a 6 times 2 over here to give us 12. And the oxygen that is here is balanced because I have 2 times 3, which is 6. So now when we look to do our ionic equation, we can see we are not allowed to separate this solid because it's solid, it's not aqueous. However, we do separate our protons from our sulfate ion, keeping in mind that we have 3 times 2, which is where the 6H plus comes from. We have 3 sulfates, so we distributed that. Over here, this is an aqueous solution, so we separate into 2 aluminum ions and 3 sulfate ions, plus our 6 waters, which stay together because it is liquid. We can then go through and cross off our common ions on either side, which happen to be the sulfate ions, and then write our net ionic equation, showing that what is actually happening is the protons are able to react with the hydroxide ion, dissolving this substance to form aluminum ions and water. So there are other neutralization reactions that can happen where we form a gas. So there are many bases besides OH minus that react with acids to form molecular, non-ionizing gas compounds. So we can produce carbon dioxide, we can produce hydrogen as a gas, we can produce hydrogen sulfide as a gas, we can form sulfur dioxide as a gas, and we can make ammonia when we react it with a base, or we can react the ammonium ion when reacted with a base to form ammonia as a gas. So here's just an example of what happens when you mix baking soda with an acid. As stated before, you're going to produce carbon dioxide as a gas, which is why it gets bubbly. So looking at a net ionic equation for the neutralization reaction with gas formation. So if we start here with our sodium bicarbonate and our hydrochloric acid, once again, we're just going to switch partners. The Na ends up with the H, or the Na ends up with the Cl, the H ends up with the HCO3. So we actually form carbonic acid. However, this is very unstable and is going to dissociate to form carbon dioxide as a gas and water. So then we look at this equation again, we separate things respectively. So what's happening? We have one Na, we have our bicarbonate ion with a -1 charge, we have one proton, and we have one chloride ion. That's our reactants. Sodium chloride can dissociate, which is why it's labeled aqueous, into sodium ions and chloride ions. We form carbon dioxide as a gas, so we cannot separate that. And we form water as a liquid. We cannot separate that. So if we go through and separate or cross off our common ions, our spectator ions on either side of the arrow, we see that we're left with the fact that the bicarbonate ion is going to react with a proton, H+, to form carbon dioxide and water. So you can set up similar equations in substituting in some sort of sulfite or bisulfite will react with acids in the same way.